Hello students, I am Brijant Kumar Patel, PGD Chemistry. How are you students? Today I am here with the discussion for class 12 for third unit, that is electrochemistry. The topic for today's discussion is the application of Nernst equation. So students, as in my previous video, I have told you what is Nernst equation. Let's revise it once again in very short. Nernst equation, it was given to understand the relation between concentration and temperature on electrode potential of a cell. So for a reaction, that is reduction reaction, Mn plus it gains n electrons and form M metal, means this is a reduction reaction. For this reduction reaction, I have told you that Nernst equation can be written as this, where E, it's a electrode potential, E0 or E0, it's a standard electrode potential, N, number of electrons involved in reaction, and Mn plus, it's a concentration of solution in which electrode is immersed. So today we will discuss about the application of Nernst equation. First application, it is to calculate the EMF of a complete cell. As you know, a complete cell means when two half cells, they are connected via salt bridge, then they form a complete cell. For that complete cell, how can we calculate electrode potential? So by using Nernst equation, we can calculate that electrode potential. See how? First, take a reaction of a Daniell cell, because it is easy to understand. Zinc plus copper ion, they form zinc ion and copper. For this reaction, you know, at anode which reaction will take place, at cathode which reaction will take place. So at anode, oxidation is taking place like this, at cathode reaction is taking place like this. So for this reaction, electrode EMF of cell, as you know, E cell or electromotive force of cell, it is the equal to the difference of electrode potential of cathode and anode. So E cell, it is equal to E cathode minus E anode, where these are electrode potential of cathode and anode respectively. For cathode, E cathode. Now in cathode, which reaction is taking place? This reaction, Cu2 plus, it is gaining 2 electrons and converting into Cu. Okay, so E cathode means E Cu2 plus, it's converting into Cu. So this is cathode, this one is anode. So the difference of electrode potentials of cathode and anode, that is equal to electromotive force of cell. Now electrode potential of cathode according to Nernst equation. Now compare this. E, electrode potential of this half cell, it is equal to E0 minus this. So in place of Mn plus and M, now we are writing Cu2 plus oblique Cu. Why? Because it's a reaction, Cu2 plus, it is converting into Cu. So for this, we can write Nernst equation as this one. The standard electrode potential of copper minus 0.059 by N log 1 by Cu2 plus. Similarly, for cathode, we can write Nernst equation as E0 zinc minus 0.059 by N log 1 by Zn2 plus. It means simply we have to put the value of electrode potentials of cathode and anode. So when we put these values, then we will try to solve this equation. So here, if you open this bracket, then you will find E Cu2 plus oblique Cu minus E0 Zn. Okay, so this will be E0 Cu2 plus minus Zn2 plus. Okay, this one is the difference minus. Now in the rest of the values, 0.059 by N, 0.059 by N, these are common. So we will take this value common, 0.059. and log 1 by Cu2 plus minus log 1 by Zn2 plus. These are the concentration of solution. So let's solve it. So as you know, this one is cathode, this one is anode. So standard electrode potential of cathode minus standard electrode potential of anode, it is equal to standard electrode potential of cell. So we are writing it as E0 cell or E0 cell minus 0.059 by n log. Now you solve it, then you will find Zn2 plus by Cu2 plus. So here this is an equation for complete cell. By using this equation, we can calculate the electrode potential of cell, or simply we can say EMF, electromotive force. So this was an example of Daniell cell we have solved here. For a general reaction, what can we write? So for a general reaction, see, E cell, electromotive force of any cell, it is equal to the standard electrode potential of that cell minus 0.059 by n, number of electrons involved in reaction, log, and here the concentration of ion at anode and concentration of ion of cathode. Anode and cathode, it means for a cell, if we take this cell Al plus Ni2 plus, they converts into Al3 plus Ni. So students, see, this is a balance equation. Okay, so this is forming a cell. So for this cell, how can we write E cell? So first you have to identify here which one is anode and which one is cathode. In very simple term, the element which is undergoing oxidation, it is anode, and the element which is undergoing reduction is cathode. So in place of anode, we will write the concentration of this Al3 plus, and its power will be equal to its stoichiometric coefficient. And the cathode, so the concentration of Ni2 plus, we will write here. So concentration of cathode and its power will be equal to its stoichiometric coefficient. It means for this reaction, E cell, it will be equal to E0 cell minus 0.059 divided by, now total number of electrons. So see here, one nickel, it is getting 2 electrons, okay, because it is converting into nickel. So one nickel, it is getting 2 electrons, 3 nickel, they will gain 6 electrons. So now the number of electrons involved in this reaction is 6. Or from aluminium, we can understand it, one aluminium, it is losing 3 electrons. So 2 aluminium, they will lose 6 electrons. So you can calculate number of electrons either from nickel or from aluminium. And in very simple word, it's a hint or it's a trick, you can say it. And the trick is, if the charges on cations at anode and cathode, these are different. If charges are different, then you simple multiply and you will gain number of electrons. Means here you can see charge is 2 plus and here charge is 3 plus. So number of electrons, 3 2s are 6. Simple word. Okay. For the reaction Mg and Ag plus, they converts into Mg2 plus and Ag. For this reaction, how many electrons are involved? Simple. It's a single plus means 1, it's a 2 plus means 2, 2 1s are 2, cross multiply just. So number of electrons, these are equal to, you just multiply the charges. If the charges are same, okay, as in this case, it's a Cu2 plus, it's a Zn2 plus. So if the charges are same, then any one charge you can write number of electrons. Means don't write 2 into 2 is equal to 4. No, it's only 2. So if the charges are same, means number of electrons are equal to the charge on any ion. If the charges are different, then you have to multiply. So for this reaction, we are going to write the equation E cell, it is equal to E naught cell minus 0.059, total number of electrons 6, then log, which is anode, here aluminum is anode. So we will write here Al3 plus, and which is cathode, it's a nickel. We will write here Ni2 plus, and Al3 plus, here see, Al3 plus, it has a stoichiometric coefficient that is equal to 2, so we will write here 2, okay, and nickel, so the stoichiometric coefficient will be 3, simple. So now this will be the E cell of the cell which is prepared by aluminum and nickel. So this one is common general reaction. Okay, for general reaction, the electrode potential of the cell can be calculated like this. Okay, second application of Nernst equation, it is to calculate the equilibrium constant, that is Kc. So the second application of Nernst equation, it is to calculate equilibrium constant. As in class 11, we have studied what is equilibrium constant. So let's discuss about equilibrium constant, and later we will discuss about the application. So for a general reaction, that is A plus B, these are nothing else just stoichiometric coefficient. So A plus B, they form C and D. So for such type of reactions, equilibrium constant can be written as, so see here how can we write equilibrium constant for such type of reaction. Equilibrium constant Kc, it is equal to the product of active masses of reactants divided by product of active masses of Kc. This Kc is equal to the product of active masses of products divided by product of active masses of reactants and their concentration term raised to the power which is equal to their stoichiometric coefficient. So these coefficients are, for C it is C, D, A and B. It means that don't take it complicated, okay, very simple. Kc, it is simply you write the concentration, molar concentration of products, and the power of the concentration or the exponent of concentration, it will be equal to the numbers in balanced chemical equation. For example, for a reaction H2 plus O2, it is equal to H2O. If you balance this equation, then this will be balanced equation. For this equation, equilibrium constant Kc, this will be equal to what? This will be equal to the product. Since we have only one product, so it will be only H2O, and the power of H2O, it is equal to 2 because this is stoichiometric coefficient, divided by, we have more than one reactants, so the product of reactant, that will be H2 and O2, their concentration term, it is equal to the power, means H2, here coefficient is 2, so the H2 power 2, O2 nothing. So we will use stoichiometric coefficient like this. So for such type of reactions, Kc can be written as, okay, in that form. So now see, we have studied about Nernst equation. For such type of reactions, Nernst equation can be written as E cell, it is equal to E0 cell, E naught cell minus 0.059 by N log this. Here remember this thing, very important. Here we will write only and only, what we will write here? Only and only ions. Don't take it here, metals. For example, if we have equation like this, H plus, Br minus and Cl2, then we will use concentration only for these two, not for Cl2. So here CdAb, we will use here only ions, okay. So in products, if there is no any ion, remember this thing, if in product there is no any ion, then here only we will write 1. If in product there is no any ion, we will write here only 1. So we will use from this equation only ions and their stoichiometric coefficient. So for such type of reactions, Nernst equation is this one. Here we know this total value is equal to Kc. So we will write Kc in place of these values. It is Kc. And for at equilibrium, you know what is equilibrium? Equilibrium, it is a state of a reaction or condition of a reaction where there is net change in the concentration of reactants and product is 0. It means the rate of forward reaction, it is equal to rate of backward reaction. Means the rate of decomposition of reactants, it is equal to the rate of formation of products. So in this way we can say there will be no change in the concentration of zinc or copper or any ion or at any electrode. There will be no change. So if there is no change, then what will be the electrode potential? We know that electrode potential, this is the difference of the electrode potential of anode and cathode. But when there is no reaction, it means there will be no change. So there will be no potential difference. In that condition, this E cell, this will become 0. So here we will write in place of this E cell, we will write 0. Why we are writing here 0? Because at equilibrium, there is no any change in concentration of reactants and products. So next see, E cell it is 0, E naught cell minus 0.059 by n log Kc. So you just transfer, you just arrange this equation. So this will be in this form. So here what is the relation or how can we calculate equilibrium constant by using electrode potential? So this is the relation. E cell, E naught cell, this is equal to this one where n is number of electrons. Or second method, for generally in place of this 0.059, this was equal to the product of 2.303 RT by F as we have calculated in my previous lecture. So here see, E cell it is equal to E0 cell minus 2.303 RT by NF log Kc. Here again E cell it is 0. So E naught cell, this will be equal to this value, transfer this side. So this will be NF E cell, E naught cell, NF E naught cell, it is equal to 2.303 RT log Kc. This is second relation between log Kc, means equilibrium constant, and E0 cell. So either of these two equations we can use. We can use this equation or we can use this equation. Both are same. The answer will not differ. So from this relation we can calculate equilibrium constant. Now come to the next. Third application, it is to calculate Gibbs free energy, that is standard Gibbs free energy. To calculate standard Gibbs free energy. How can we calculate? So in class 11 in thermodynamics, we have studied that del G naught it is equal to minus 2.303 RT log Kc. So from here, put the value of this thing 2.303 RT log Kc. The value is NFE0 cell. So here we will write del G0 it is equal to minus NFE0 cell. So from this equation we can calculate standard Gibbs free energy. Okay, here N is number of electrons, F is Faraday constant, and E naught cell it is standard EMF, electromotive force of cell. So in this way, these are three applications of Nernst equation. In next video, we will try to solve some numericals based on Nernst equations and their applications. Thank you, students. Thank you. हो गया इतनी क्या कर